All right, let's get started. So some of you are waiting for me to make a decision on the course eval, so I figured I'd just do this live. And unfortunately, the suggestions are kind of, I just won't even use a word. Yeah. No. No, in the previous two lectures, I said if you have suggestions, put them in the damn Piazza post. You can't just shout out suggestions. And a lot of the suggestions that were shouted out aren't on the Piazza post. You're driving me nuts with this stuff. I'm only going to consider stuff that's on the post right now. And W, don't know what to do with that. Better fill those out, sure. Homemade cookies at 90%. 5%, this is the highest voted one, just 5% straight up added to your final grade. I'm not going to do that. It's got to be something that you earn, not just a flat up plus 5%. I understand why this is a popular choice, but I'm not going to do a free one. If it's something where you can earn any points that you missed, if you can make those up somehow, I'm fine with. But just straight up free points. And I said I'm capping the objectives at 3, so 4 objectives, 5 objectives. I already explicitly said that those aren't going to happen. Kind of like this one, but it got no support. And support on the comment that says no. So definitely not doing that one. There's no universal support. And this one also got no support. I said multiple times I was open to some lecture question thing, but I kind of oppose it in the sense of it's only rewarding students who haven't done what they're supposed to do all semester. So since this didn't get support since 3 hours ago, nobody else posted it, even though we discussed it twice in lecture. I'm assuming there's no support for any lecture question amnesty either. So unfortunately, there's really no suggestions here. I guess the plus 5% is the only one that wasn't just outright ruled out in lecture. So unfortunately, there's really not much I can work with here, except it's the only one that actually is a valid suggestion. Yeah. No. So it's the only thing I could work with here. Oh, how do I even read this? No. When it'll be chocolate chip. I like chocolate chip. On what day? When do evals close? Does anyone know? Does it close before the last day of classes? On the last day? So my only choice would be on final exam day. So I would bring homemade cookies to the final exam. We have presentations during the final exam time. So if you're not presenting but you want cookies, you'd have to show up anyway. All right, I'm locking in. I'm committing. All right, so that's going to be the 90% incentive. Since it's not attached to anyone's grade, we'll see. Usually the grade things are the strong incentive to get to 90%. So if we get to 90% without a grade incentive, yeah, I'll bring in cookies. I'll spend the day before the final exam cooking bacon. Yeah. It's tough to, yeah, I'll do this. It's tough to refresh the page, but I'll have to switch away and do it. Because I'm in the student view, I complained about this already in the lecture, but I'm going to complain again because it really pisses me off. I'm in student view, so I preserve everybody's anonymity if you post anonymously, but if I refresh the page, it says, oh, you want to be in instructor view again. So I can't refresh during a lecture, but let's see. Yeah, you wait till after everything's said and done to do this stuff. I'm not going to entertain new ones. I don't know, unless there's a really good idea. Weight our best homework at 20 and worst at 10. If that was suggested earlier, that would have been a good one. Lectures for second to last week be remote. There's the second to last week, there's no lecture questions. So if you're worried about the lecture questions, you can not be there. You can just watch the video later. Panopto posts the videos right after lecture, so you can treat it as remote.
Jesse, you're still in instructor mode.
I'm still in instructor. Oh, fuck off. Piazza. No, I'm in student mode. What? Why? Piazza. Well, I hope nobody wanted to be anonymous because Piazza's making it really hard for me. I'll just read them like this. 100% Twitch gaming live stream with Jesse. I've done that in the past. I played Portal 2 on stream. People asked that for an incentive. Jesse pays for everyone's tuition at 90%. I think it'd need to be like 101 for that one. Okay, hear me out. For 90%, the project percent drops to 20%. It's now, or 15%. It's now 20, and lecture questions become 15. No, I think the 20 is like the minimum I would do for the project. Again, if that was suggested earlier, I would have put it under more consideration. But 20% is the minimum I want the project to be worth. If it's only 15%, the problem, I've had really low percentages for projects, sub 20 for projects in the past, and it's really easy for one of your teammates to just say, I'll take the 15% hit and not help you out at all. So I don't like going below 20. 20s, there's enough meat there that the slackers are less tempted to just completely blow off the project. Anything less than 20, you're going to get that symptom. But yeah, some of these, if they were posted earlier, I mean, I've been talking about this for the last 2 lectures, trying to urge people to make suggestions. Yeah, you have to help me make the cookies. No, you earn the cookies reward by eating the cookies. You actually have to expend some effort to eat them. I'll probably make you walk down to the front of the room to grab one, so it'll be some work for you. You got to earn it. So I actually did build a Piazza browser extension to do some of that. I want, like it just tells me your name, but I want your UBIT, so I built an extension to do that, and I could extend that to keep the anonymity as well, but I don't even have that installed on this browser. But yeah, it's getting more urgent. If I ever want to show Piazza again in class, I have to build an extension, which it shouldn't come down to that. How does let me get Piazza out of here and go back. Oops, wrong button. How does the project grading if a teammate drops? So this is coming up more often. I think there were 8 resigns in the semester, 8 official resigns, and probably usually a few more students who won't do anything at all, but just haven't resigned and are taking the F. So in those situations, if you have a teammate who hasn't helped at all or has resigned the course, you get their points. So I'll take whatever the project grade is. So you get 1 project grade as a team, and then whatever points that teammate earns, so say you earn an 80 on the project, and you have 5 team members, one of them resigns, that student's 80 points gets distributed among the other 4 teammates, so you would all end up at 100 for the project. So if you have somebody who dropped or resigned, or if you have 2 teammates who dropped or resigned, you absorb all of their points. So you have a lower target to get 100 on the project. So I turned something that should be a really, really detrimental thing to the project into something that kind of ends up benefiting you in the end. I think that's more than fair. I think that overcompensates for the lost teammate. As long as you lose them early enough in the semester. If you lose them like right before the project deadline, if they don't resign and then they, but by then you should know that they're not doing anything, I think. I've had teams before where it's a team of 4 and 2 students resign, and they're aiming for a 50 for their 100. That's all they need to get it because they're going to double their score. I don't allow any grades over 100, so if you get 100 and somebody resigned, you don't get 120 or 133, depending on how many teammates you had. It does cap at 100. But that's how I resolve that. I think that's pretty fair. I don't think anybody's complained about that in the past. Because it does suck when a whole teammate drops. Yeah. If you have a team of 4 or 5 and 4 of your members drop, and you can manage a 20 on your own, yeah, that's 100. I'd stick with it. What are we doing? Homework 4 roadmap. You can do through objective 4 now. Nothing's slowing you down with homework 4. We just had the homework 3 deadline, and I got the regular flood of emails asking for extensions. If you're asking for an extension on homework 3, the answer is no, unless you have some really severe documented issue that happened. Like if you were in a coma for the past 2 weeks and you got a doctor's note for that, yeah, I'm going to give you an extension. I was a little bit generous with homework 2 extensions because it was the first difficult homework. I was a little sympathetic, like maybe you didn't understand how much work this homework was because homework 1 wasn't much work. I let that get to me a little bit. Homework 3, by this time, you know how much one of these homeworks takes. So no, I'm not going to give you an extension just because you started at the last minute and stuff. I know way too many of you start late. There's no excuse on homework 3 to still be starting that late. So no extensions on homework 3. Whatever you submitted before the deadline, that's it. Yeah.
Oh, I was just wondering, the authentication tokens and just kind of all of the cookies, are they stored in the HTML like the XSRF tokens were?
No. No, all your cookies and stuff, they're not stored in the HTML. They're stored, the browser will store them separately. If they were in the HTML, attackers would have an easier chance of getting that stuff. We don't want to make anything easy for them. So you can do up to objective 4 this time. Objective 5 is going to take us a week of content to talk about. It's going to take quite a bit. So let's get started on HTTPS. Our goal is to get this lock icon, to get security, encryption on our sites. So let's talk about it. Not cookies, encryption. Oh, and thank you for everyone, all the random lead generated teams who've been sending me their URLs for the GitHub repos. There's still a few teams who haven't. At this point, I would assume they're not attending lecture and they're not in the room. But if any of you are and you haven't sent me your repo link, maybe do that. I don't know what else to tell you. But we're going to start looking through your checkpoints and, of course, homework 3 grading. I didn't realize. I'll talk to the TAs. We have a meeting on tomorrow night. I kind of doubled up their workload on this, so we'll have to talk about how we get these done. Homework 3, the deadline will still be for grading, getting your grades out 1 week after. If that has to come to the delay of the report checkpoints, I'll prioritize homework 3 grading and tell the TAs to prioritize homework 3 grading over project reports, but I'll talk to the TAs about that tomorrow. And I think I have to move this deadline because unless this form is live, maybe I just checked this last lecture. I'll have to move this deadline because I haven't even set up how to sign up for a presentation yet. So I'll move this back probably till the Wednesday after break. That'll still give us time to get the schedule up and running, up together. But I'll move this deadline because I've been dragging my feet on getting the signing up for a time ready. Yeah.
What's new that you're moving?
The sign up for a presentation time. On the schedule, I have it due in 2 days, and I'm not going to get it ready right now. Even if I got it ready right now, that's not enough time. That's not fair. Honestly, I can't tell what happened in the past few days. Tell me about it. What does that mean? When grading homework, will the TA go through every objective, even if an earlier one didn't? Oh, yeah, they're supposed to. If that doesn't happen, just follow up with the TA after grades are out, and we'll get that. Even if you mess up an earlier objective, you should be able to get the later ones. As Nicholas said, Nicholas already answered it. And with the presentation deadline, so when I do get the form up and there is a sign up for a time deadline, if you don't make it by that deadline, I just give you a random time anyway. So any teams who didn't sign up, you get a random time. So it's not the end of the world. It's not like you lose points or lose your opportunity to present. But I still want to give you ample time to choose which time you want. It is important for a lot of you. If you are leaving town before the final exam time, you want to make sure you sign up early and get something during the last week of classes, for example. So I want everybody to have ample time to be able to make those decisions, talk to their team and everything about it. Great Objective 5 first. All right, let's get into it. So we've been using HTTP all semester, which is great. We like HTTP. It's how the internet works. It's how the internet runs. The issue with HTTP is that it sends all the information in plain text. In plain text, including your passwords, which, well, okay, that plain text password is zipping through the internet. Big deal. Like, who's going to be able to access that? Well, a few people. Your ISP, if you're working from home, or UBIT and Tier 1 networks on campus, well, Tier 1 networks anyway. UBIT running the network, they have access to all the routers. They can view all the information zipping through the wires if they so desired. Your ISP at home, obviously, they have access to everything. They run all the equipment. They run the network that you're plugging into, literally plugging into with your router. They have access. They have full access to see everything that you're doing online. And Tier 1 networks, whether you're on campus or off, your ISP connects to Tier 1 networks. UBIT, the UB network plugs into a Tier 1 network. The Tier 1 networks always have access to everything you're doing, even if you never signed a contract with them, even if you have no idea that you're using the Tier 1 networks. They have access to all of your information. Okay, maybe you're still not too worried. There's a reasonable assumption that all three of these groups we can reasonably trust. But also everyone within Wi-Fi range of your device has access. Do you trust everyone in this room and people out in the hall? Apparently some yeses. Okay, well, I guess we don't need encryption then. We're done. This is the last topic of the semester, so see you later. See you in the spring. Hopefully you don't trust all those people. At best, you'll trust them to be lazy enough to not do anything, to actually care. But anybody running Wireshark, they can see all of your information zipping through the air. We call it packet sniffing. You grab the packets out of the air, you assemble them, realize that they're HTTP messages. You see the destination IP, the sender IP, the headers, the content, all that stuff, the body, all that stuff is just there. Zipping through the air, going to this access point, or that's not an access point, is it? Going to this access point, or this access point, or that access point, or that. Wow, there's 4 in this room. Everybody can see that information. When you send information over Wi-Fi, like there's no beam of signal going from my wireless card beaming over to that device, that access point. It's not how it works. Instead, this is going to broadcast and say, hey, everybody, here's the information I want to send. And then that access point knows, hey, whoa, that information is for me. I have to do something about that because that device is connected to me because we kind of agreed that that's what we're doing here. I'm going to listen for those signals on this wavelength and then forward them to wherever it's going. But that signal is also hitting all of your Wi-Fi cards. It's hitting every one of them. And your card is saying, this information ain't for me, I'm just going to throw it away. Well, if you install software like Wireshark, Wireshark is going to let you see everything that's hitting your wireless card. You can see everything. It's all out there for everybody to read. This is why it's always recommended if you're in public Wi-Fi, like you're at a McDonald's or something using their Wi-Fi. Everybody else at that McDonald's can see what you're doing if you're using HTTP. Of course, we're going to encrypt. That's what we're building up to, so they can't. But that's, if you're using HTTP, that's the danger. Yeah?
So the information zipping through the air, is that ones and zeros, even though it's
Oh, yeah.
not cables? And like, if someone's tapping into that, how would they know where something starts and something ends?
Well, the software will know where something starts and where it ends. So it is all ones and zeros even when it's wirelessly, but they're going to know the same way that you know if it's over a wire.
The software that's reading.
Like you use Wi-Fi, like your laptop and that access point are communicating with Wi-Fi. Like they know how to do it. You'd have to talk to an electrical engineer to figure out exactly how, but it's all wavelengths on a certain frequency, and those wavelengths will tell you if it's a 1 or a 0. It's upsetting? Wait, what part? That you can use Wi-Fi?
Yeah, it's not just between point A and point B.
Oh, that it's, yeah. Mm-hmm. But it's a reality. If you don't like it, plug into all your routers, which I guess that's hard to do on campus, but your password is ********. Oh, goodness. This includes your passwords. Does anybody have any site? I love doing this because you can name any site ever that requires a login. Does anybody have any site ever? Wizard 101? It's not going to be porn, is it? Just click it. Trust me, bro. I'm going to go to my network tab. I'm going to play free now. Where's my login? I need a login here. Username, Hartloff. Login. So I sent the login request, and if I scroll down and see what was actually sent, my plain text password that I typed in. Passwords are sent in plain text. Why not hash them, you say? Why wouldn't I hash this? On any site, just any site. I've never been to this site. I didn't check this out before lecture and have a plant in the audience yell it out that we agreed beforehand. That didn't happen. Any site is going to send your password in plain text. Don't worry, it's encrypted. That's where we're headed on this lecture. But it will be plain text. Why?
Because a hash password, it requires using a specific function to hash it so that if you don't know what's going to be like on the other end, and it's just if it's hashed on the get-go, everyone will know that hash, so if they get it, then you won't even be able to like store it securely.
You also could solve it.
So a few things. In the other comment, you couldn't salt it. So one, it's the JavaScript of this site that we're using. So in that JavaScript, hash function's there. Same hash function for everybody. Problem solved. Couldn't salt it. I can just generate my own salt and send the hash and the salt, because salts are plain text anyway. They're out in the open, in the database at least. So why not do all that? We could have that in front-end JavaScript, do all the hashing and salting and all that stuff, and then send something a little more secure over the wire. Yeah. Hashes can be brute force. Mm-hmm. But they can be brute force. I mean, this can be brute force. It's just my password. So if I have a really strong password, the hash shouldn't be able to be brute forced. So why not just say, hey, use really strong passwords, we're going to hash it front end, and then before it leaves your laptop, it'll be only a hash. And somebody has to crack that hash, which they can only do if you have a weak password. So why not do that? It's got to be better than just plain text, my password right there. Yeah. Yes. Yeah. I'll get back to that one. Let me go for it
Front-end
first.
JavaScript can be modified by anyone.
Yeah. So the JavaScript can be modified by anyone, but if you modify that JavaScript and send the wrong thing, you just don't log in. So you're only screwing yourself on that one. You could remove the hashing yourself and then just get less security, I guess. So the issue here is that if I hash first and then send the, yeah.
I just have a quick question. If the Wizard 101 site is an HTTPS, how can you use the plain text password?
So I'm viewing it, I can view it on my device because I'm viewing it before it was encrypted. But as soon as it left my laptop, it was encrypted and then sent. So if you sniff this packet out of the air, it'll be encrypted. But I'm still allowed to see my own packets through the browser window. Yeah.
If they sniff the password that's already hashed, they can just send that.
Yeah. Yep. So we got it out there. So the problem with hashing and then sending is the attacker doesn't need to know my password. They just need to know whatever leaves my laptop. If what leaves my laptop is a hash and the server's expecting a hash, that hash is effectively my password. So the attacker grabs that hash. They don't have to break that hash. They're just going to send that hash to the server. Done. Server's expecting, when I legitimately log in, the server's expecting that hash. If the server's expecting that hash, that's what the attacker needs to send. They never need to crack my password at all. So if we can't get an extra level of security here, why not just send the password plain text? There's nothing we can do front end to add security to this. We can only just obfuscate things a little bit. We can't actually add any security, any level of security here through some front end JavaScript. Because whatever we do, no matter what we do, whatever leaves my laptop effectively is my password because that's what the server's expecting. The attacker's just going to send whatever that is. And it doesn't matter how much computation was done. We started with some actual password and mixed it all up, took the hash of it 57 times, and then sent whatever leaves my laptop. That's what the attacker is going to send to the server. And that's what the server is expecting. And that's what's going to authenticate me or the attacker. So out there in the real world, passwords are not hashed, client side. They're always sent plain text. There's one example that I found where it wasn't plain text. Bank of America's mobile version of their site does some form of hashing. I think it's an MD5, but I don't think it's used for security purposes. I don't know why they use it. So it's weird. The window, if you use it like this, it will send plain text passwords. And then if you resize it to the point where it hits the mobile version and send the same form, I think you have to refresh and get the mobile version of their site, and then send it. It sends an MD5 hash. It's really weird. It's the only example that I was able to find where this isn't the case. Yeah.
So if passwords are sent in plain text, on the server side, with that little add server route, it's processing a post request. It pulls the plain text password out of the header after it's de-encrypted, which I'm going off of now.
Mm-hmm.
And then that's stored in a local variable in the server just for a second while it's like tossed over to the database for authentication.
Yes.
Is that secure? Is it allowed to be in that little local variable just for a second?
That's how the world works. Yep. Whether it's secure or not, well, it is how the world works, though. So when the server gets any login or registration, the server is handling plain text passwords. And your server won't be any different for the homework. This is how the world works. This is how things work, is they will be handling plain text passwords. You never store plain text passwords, but you do handle plain text passwords. So there are some attacks that can observe that login process and steal plain text passwords at that point. So somebody can inject some code into that process. They can grab plain text passwords. If a sysadmin goes completely rogue and wants to steal your passwords, they'll put some code right there and start grabbing passwords. But this is what's called a live attack. They can only attack you if you're actively using the site. If you have a site you haven't logged into in 5 years and your hashed password is sitting in a database, they can't attack that. But when you go to log in, as that action is happening, they can recover that plain text password. So there is still some security concern here, but it's not it's something to be aware of, but it's not something that, it's just how we do authentication. Because even if we were hashing and then sending, it's the same issue we just talked about before. Somebody's going to observe that process, grab the hash, but that's what the server's expecting anyway, so that effectively is your password. There's really nothing we can do at that point. Plus, if we did anything to the password and to the point where the server's not handling plain text passwords, how are you going to verify the strength of that password? You wouldn't be able to. Somebody could just have the letter A as their password. It gets hashed, and you would never know that it's a weak password. So a few reasons to handle plain text. That's a big reason to handle it is you can enforce your password strength rules. Because if your password strength rules are only enforced in JavaScript on the front end, well, someone's going to go in and just delete those things. I've tested sites before where I took the JavaScript that was checking password strength and just replaced the body of that function with return true. And then had a password of like 1. And I forget what site I was doing that on, but then it worked.
All that's got to be on the back end, everything checking the password?
Yep, it's got to be on the back end. Because the front end cannot be trusted. You cannot trust your users ever, ever, ever. They can modify anything you send them. They don't have to use your front end, anything that you gave them, they don't have to use that. They can write all of their own stuff. Can't trust that. So the way it works these days is you have both. You have the front end JavaScript that's checking the password strength. So you can have the nice, like the bar goes red, yellow, then green. Like we have those checkers that are responsive and the checklist that automatically updates. You want that to be nice and responsive, so that's front end. But once you send the password, the server should also be checking that password strength. You need to have checks on both ends. Well, the front end if you want just for a usability feature, and the back end for your actual security. But you gotta, if you're going to have front end, you got to also have back end. Yeah.
So if you wanted to disable front end protections, would you just kind of take a look at the GET request that the JavaScript came in, and then just kind of engineer it from there, looking at the actual code?
Yeah. Yeah, and you just go to sources, find your JavaScript.
And just see what it does with it.
Yeah, just go to the JavaScript. It's going to look like this. And then you click this button. Oh, not that button. This button to make it look a little better. And then you just edit it. Oh, how come I can't edit it? Do I have to enter edit mode or something? I don't know. I don't know what I'm doing. Why is it not letting me? But anyway, you can edit JavaScript. I've definitely done it before, but fun fact, I haven't really talked about it, but you have a debugger as well. You have a full debugger in your browser. It's helpful when debugging front-end stuff, but since we don't do front-end stuff, I don't really talk about it in this class. But yeah, anyone within Wi-Fi range, if it's HTTP, they have your plain text passwords. Just how the internet works, we send plain text passwords all the time to servers. So we need a better solution. That solution is, we'll slap a little S right here and call it a day. HTTPS, now everything is encrypted from from below the TCP layer or above, depending on which way you think of your network stacks. But the HTTP requests will be encrypted. HTTPS stands for HTTP over TLS. Some people call it HTTP secure. If you want to call it that, whatever. I'm fine with that. But it's technically HTTP over TLS. So we have an extra layer in the network stack, which is going to add the encryption for us. So with encryption, and we'll get back to HTTPS Wednesday. I'm trying to remember all of my slide order here. I think Wednesday. But we need to talk about what encryption is first. So with encryption, we want to hide messages. I have some plain text message, or even, this could even be at the byte level. I'll talk about text, though, in this. No, I do say it right there. But this plain text can be any message in any format, just whatever information we want to encrypt. Just since I kind of stepped on my words there, we call it plain text in the world of cryptography. It can be just any arbitrary bytes, though. But we just call it plain text because that's what it's called in this world. The plain text is going to be the unencrypted message that you're sending. You want to encrypt that into what we call crypto text. Send the crypto text over any channel that might have an eavesdropper on it, and then the receiver is going to decrypt back into plain text. So this is a bit of vocab that we use in cryptography. We're talking about encryption. Plain text encrypted to crypto text, and then decrypted back to plain text. Yeah.
So requests and responses are both encrypted?
Yes.
So the HTML,
Oh,
that's
yeah, absolutely.
payload, that's encrypted.
Yep. Yeah, all your WebSockets, yeah. All your WebSocket frames, your WebSocket handshake. RTC, maybe? Yeah, I believe RTC has to be encrypted. It's different than what we're doing here. It's over UDP and stuff, but it'd be the same idea. I believe WebRTC has to be encrypted, or else the connection's rejected by one of the peers. I believe. I don't remember off the top of my head though. So I want to send a message. I encrypt it. We get some crypto text. The receiver decrypts, gets back to the plain text, and nobody besides the intended receiver should be able to make any sense out of this garbage. That's our goal with encryption, and we'll get there. We will get there with encryption. Specifically, we're going to talk about public key encryption today. So with public key encryption, we generate a private key and a public key pair. So we're going to generate these two keys. The public key, as the name implies, is public. We share that with anyone. Anybody wants my public key? You can have it. Share that public key with every single person on the planet if you want. Every single device can have that public key. Private key, as the name implies, private. I keep that in my pocket and I don't tell anybody my private key, ever. When somebody wants to send a message to me, no, that's backwards. Oh my goodness. I'm going to cheat. I'm going to read my slide. So when somebody wants to send a message to me, they encrypt it with my public key. So there's encryption and signing, and sometimes I get them backwards if I only have a few seconds to think about it. So they're going to encrypt with my public key, send the crypto text to me, and that crypto text is such that only the owner, only the person who possesses or anyone who has knowledge of the private key can decrypt that crypto text. So you want to send me a message, here's my public key, encrypt with my public key, and then only my private key can decrypt. So you can share that message, the encrypted crypto text, with everybody on the planet, and even though they have my public key, they can't decrypt it because they don't have my private key. You send that message to me, and you know that I can read it, but nobody else can read it. Yeah.
What's the point of encrypting requests? Responses?
Because you don't wanna, you want to be private.
Well, they're decrypted with the public key.
So if I say, hey server, I want to upload this really compromising material, and the server says, okay, I uploaded that really compromising material. I don't want that response being known. Like, it's a privacy thing. What if I send, hey, send this other person a message, the server sends that person a message unencrypted? Like, I want that to be encrypted.
No, like, what's the point of encrypting it if you're decrypting it with the public key that everyone has?
That's not how it's working. You encrypt with the public key. You decrypt with the private key.
When you send to the server, you look at the server's public key, I guess.
Yeah, we'll get to the whole thing. You're stopping me on slide 1. There's a lot coming up. But if you want to, so that is a big question though, is how, when the server is sending information to me, do they encrypt? Because I didn't give a server my public key. You don't generate key pairs on the cloud. But we'll get to all that. So I want these properties that crypto text, if you have crypto text that somebody sent to me and my public key, you need to not be able to decrypt that crypto text. And any information that they have, I forget what the two things. And given my public key, they can't determine what my private key is. These two keys are inherently linked. They'll be mathematically linked, as we'll see in a second. But given my public key, which everybody can have, you can't figure out what my private key is. And given the public key and crypto text, you can't get the underlying text. You can't decrypt. These are the properties we want. Math is going to help us get there, specifically RSA. So this algorithm is going to give us a way to generate key pairs, encrypt with the public key, and decrypt with the private key. Everything that we want. And it's math. I'm not going to go step by step through the math, but it's math. We're going to generate or randomly generate, as random as we can get, two very large prime numbers, P and Q. Run them through some math, and that's going to give us values D, E, and N. E, and N are the public key that you share with everybody, and D is my private key. Technically, N is kind of part of the private key as well, but N has to be public already, so N is part of the public key as well. But D is the one value you need to keep private, and then everything else you just throw away. So D is a number, and it's a number you don't share with anyone. To encrypt a message, you take your message M, and this is where we see that it's bytes. You encrypt bytes as a number. Raise it to the power of E, the public encryption key mod N, and that's your crypto text. To decrypt, you raise the crypto text to the power of your private key mod N, and that'll return your message again. So the math is set up in a way such that the message raised to the power of E times D mod N is going to get you back to the message. That's what that math is guaranteeing, that those, like E and D are inverses in this way that they'll cancel out when M is raised to both E and D mod N. You'll get back to whatever you started with. And conveniently, multiplication right here is commutative. So we encrypt with the public key and decrypt with the private key, but we can actually do this the other way around too. I could encrypt with the private key such that everybody on the planet can decrypt that message, so I have no privacy at all. But you could decrypt with the, decrypt in quotes, with the public key to be able to read the message that I sent, which seems pointless because everybody can decrypt that message. But this is very useful in what we call signatures. So if I want to sign something, I want to digitally sign something, I'm going to take my private key, sign it. That's why I put encrypt in quotes, because it's actually a signature. I'll sign that with my private key and then send it out to the world. There's no privacy here. Everybody can read that message, but what you do get is a guarantee that I'm the author of that message. Because if you can read it, if you can verify the signature with my public key, you know that only somebody who has possession of my private key could possibly author that message. And if I'm being careful with my private key, that should only be me. So you can verify that that was me who sent that thing. So digital signatures is a nice byproduct of this public key encryption system when we use RSA like this. Since this is commutative, it doesn't matter which order you raise these power to, either the private key first or the public key first. The other one will be able to get back to the original message. Very handy. Very handy thing to do. Math is stupid. But what about a brute force attack, you say? If I have your public key, that's what I need to generate crypto text. Somebody sends me a message, you grab that crypto text, you have the same public key that they use to generate that crypto text. Why not just try a whole bunch of texts until you get one that creates the same crypto text, and then you know what text they sent? So for example, if I ask somebody a yes or no question, you have 1 bit of entropy. It's either going to be yes or no. I grab that crypto text out of the air, I take the public key, I try yes, I try no. One of those two is going to match the crypto text, no? Same exact attack that we had with hashing, we just use the public key instead of the hashing algorithm. Well, we actually have protection against this. We use what's called a padding algorithm. So instead of just encrypting the message that we're going to send, we're also going to add a bunch of random garbage called padding and some information encoded using a protocol in a way that the receiver is going to understand to say how many bytes of random garbage there is attached to the message. So I have my message, the number of the amount of padding, and then the padding itself, which is purely randomly generated, not purely RNG, but randomly generated padding. And then I encrypt that. So now the person decrypting this with this brute force attack has to guess that padding. This isn't like assault where it doesn't add entropy. This padding adds entropy. We get entropy out of that because all of that padding has to be guessed by the attacker, or else they're not going to get back to the original message. And that padding is not stored in plain text. There's no way to just get all this padding. It's just randomly generated. Every single time you generate a crypto text, you're generating a new, different padding. So every time you encrypt even the same message, it's going to look different in the crypto text every single time because we have these padding algorithms. And when the intended receiver gets this, they'll decrypt, they'll get the message, it'll say this much padding. You just ignore the padding. It's not important, you just ignore it all. And then you get your message. But if that's a yes or no answer, the attacker's not, you encrypt yes, you encrypt no, neither of them match because you didn't have the padding right. You have to guess every bit of that padding correctly in order to get back to the original message, which ain't going to happen. You're not going to guess all that padding. So even with one bit of entropy in the message, we can add any amount of padding we want and get way over our 80 bits of entropy needed to call it secure. So even if you're sending one bit of entropy in a message, we can be secure with encryption. As much entropy as we want. But there's another problem, you say. E, D, and N are all public. N is the multiplication of P and Q. So if I just factor N, I got P and Q, and then I can just run through the rest of this algorithm. The only choice here is choosing E, but I already know E. It's the public key. And I can just compute D the same way you computed it when you generated these keys. Math to save us here? Well, we hope at least. That factoring, as it turns out, is extremely hard. We don't have an efficient algorithm that can factor the multiplication of two large primes, or two any primes. So if the primes are large enough, we don't have an algorithm that will factor that n before the sun's going to burn out. The universe will be gone. Even if you use every single computer that exists on the planet right now and every computer that's ever going to exist ever, the universe is still going to be gone before you're done factoring n for any reasonably large key. If you got a 4K key size, you're not factoring in. Nobody's factoring in. Until we get quantum computers. I shouldn't say any computer that will exist, because once we get quantum computers that are efficient and large, then we can do that. But for now, factoring's hard. But also, when you have crypto text, well, crypto text is just the log base E. Oh, I always get this backwards. The log base E mod n, which is called the discrete log. You just compute the discrete log of C mod n, and that's going to give you m. And luckily, discrete log is also hard, we hope. So because these two mathematical operations, both of which would completely break our crypto system, are hard, at least we have no known algorithm to efficiently compute either of these, discrete log or factoring, we rely on that for pretty much the entirety of encryption right now. So if you have an efficient algorithm to solve either of those, then I don't know, you have a lot of power. Choose what you'll do with it. But we're running out of time. I'll finish up these slides next time. but we got to get to the thing. Have a great day. I'll see y'all Wednesday.